It's section 4 of chapter 9. We're going to be finishing up finding inverse expressions, or inverse equations and inverse functions. This time around, we're going to actually find how to do that algebraically. We're no longer going to be dealing with that chain thing, because the chain way of doing the inverse operations in the inverse order has an inherent weakness. So first, I want to do a brief little recap of what we just got done doing. If I have the function f of x equals 2x cubed plus 1, and I told you to find the inverse of that function, what we would do is we'd say, okay, well, the first thing I would do to the x is I would cube it. Then after that, I would multiply it by 2. Then after that, I would add 1. Therefore, the inverse, I'm going to do the inverse operation, so I'd subtract 1. Then I would divide by 2. And then I would cube root. Therefore, the inverse function would be defined as, well, first I'm going to subtract 1 from the x. Then I am going to divide that all by 2. And then I'm going to take all of that and cube root it. Here's my inverse function. And that is how I've been telling you to find inverse functions. And that is a great way as an introductory to inverse functions, as to what they are, how to visualize them, and how to generate most inverse functions. But it has an inherent flaw baked into the methodology and the approach. I'm going to show you a problem right now that you cannot use this on. What if there are multiple x's? What am I going to do first to that function if I'm plugging in a number for x? Am I squaring it, or am I multiplying it by negative 12? The truth is, you're doing both simultaneously. You cannot use that chain methodology on a problem that has multiple x's that do not combine together. So what we need to do is generate a new technique, a new algebraic technique to find inverses that will always work. And in order to do that, we're going to rely on what we did in the previous lesson. We're going to figure out the graphical interpretation and see how that can translate to the algebraic approach. So when we did inverse functions graphically, we noticed a few features. One of the features that we notice is that a function and its inverse are reflections over the line y equals x. We also noticed that all of the coordinates for the function and its inverse were inverted. That is to say, if you have the coordinate a comma b for the original function, then there by default had to be a coordinate b comma a for the inverse. So the x and y values swapped. And I kind of came up with these symbols, that x is equal to y and y is equal to x, and the x and y swap. I didn't pick those little symbols nonchalantly. This is the algebraic approach. If you want to find the inverse function, graphically, you take the x and y and swap them. Algebraically, we're going to do the same thing. If I give you a function like y equals 2x plus 1, and I want you to find the inverse of that function, I am going to take the x and y and make them equal to each other. Or another way of saying it is I'm going to take the x and y and swap them. So this function, if I want to find its inverse, I'm going to rewrite it as x equals 2 times y plus 1. And because I want this as a function, I'm then going to simplify that equation such that I'm going to turn it into y equals something in terms of x. So I'm going to subtract the 1 to the other side and be left with x minus 1 is equal to 2 times y. I'm going to divide both sides by 2. And that'll give me the equation. I don't have enough room, so I'll put it off to the side. The inverse equation, y is equal to the x minus 1 all over 2. This is the inverse of that function. And I did it without doing any kind of chain. I did it without looking at any kind of graph. This is how you can algebraically always produce an inverse function. This does not rely on the fact that there only be one input value for x. You can use this technique even if there are multiple x's. I'm going to do 2 problems, and then I'll leave you to work on it on your own. Take special note, the second problem I'm going to do is the problem that earlier I said that we were not able to do using the chain method. Additionally, for problem number 1, I have g of x equals 2 times the quantity of x minus 1 quantity cubed plus 5. Realize that g of x is just a fancy way of saying y. I'm just giving it a name. The name is g. It has x in its function. So if I want to find the inverse, the first thing I'm going to do is take the x's and y's and swap them. So this is going to turn to x equals 2 times the quantity of y minus 1 quantity cubed plus 5. Now, I'm going to spend the rest of this problem trying to isolate the y value, trying to get y by itself. So I get y equals equations with x in it. So I'm going to subtract 5 from both sides. That'll leave me with x minus 5 is equal to 2 times the quantity of y minus 1 quantity cubed. I'm then going to divide both sides by 2 to get x minus 5 all divided by 2 is equal to the quantity of y minus 1 quantity cubed. Got to get rid of the third power by cube rooting both sides or bringing both sides to the 1/3 power depending upon what kind of notation you want to use. The cube root and the cube would eliminate, so you're just left with the cube root of x minus 5 all over 2 is equal to the quantity, oh, actually no more quantity, just y minus 1. Add 1 to both sides. I like writing my y values on the left, so I'm going to rewrite it towards y equals instead of something equals y. Y equals the cube root of x minus 5 all over 2 plus 1. This is acceptable. I will not mark you off if you write this. But technically, in the math sector, a mathematician would scoff at you for writing your answer like this. Because, while this is correct, it's not using the same notation we like. Because if I say y equals that function, it sounds like just a normal everyday function. What we should write is g inverse of x. Because writing that inverse function notation immediately, like if I erased the rest of the problem and I just told you that, that would be enough for you to know, oh, that function has an attachment to some other function we call g. That attachment is their inverses. You might not know what that inverse is, but by looking at that and reading inverse notation, you'll recognize that that function is connected to something else. If you just write it as y equals, you don't get to read that connection. So I would ask, and this will help you later on down the road, that if I give you a function in function notation and ask you to find the inverse, your answer should also include function notation, and it should state that we're finding the inverse. That way I see that you're understanding the connection between the two functions. Problem number 2. First step I'm going to do is take the x's and the y's and swap them. This is going to turn into x equals 4y squared minus 12y plus 9. This problem's going to get a little spicy. Because ultimately what I want to do is I want to simplify this problem in such a way that I'm going to be left with y equals something. Our issue is we have a y squared and a y to the first power that don't combine together through addition and subtraction. That means we're going to have to find a way to turn them into one solid piece. There's a technique that I showed you. It's a technique that we're going to utilize called completing the square. So I'm going to rewrite this as x equals 4y squared minus 12y. I'm going to add a number right here such that that will all factor into something squared. Then I'm still going to use that plus 9, and then whatever that number I have that I'm going to add in black, I'm also going to subtract at the same time. I'm going to draw an area model such that the bottom right portion is missing and I'm going to say that that area model has to be a square. The 4y squared goes in the top left box. Whatever's in these two boxes has to be half of this. So it's going to be negative 6y and negative 6y. Therefore, the outside pieces will be 2y and 2y, because they have to be the same, and then negative 3 and negative 3. That'll combine together through multiplication to get me a positive 9. That is the number that is going to go here and here. So I'm going to add 9 and subtract 9. These first three pieces, the 4y squared minus 12y plus 9, factor to give me 2y minus 3 times 2y minus 3, which is the quantity 2y minus 3 quantity squared. And in this problem, the two outside pieces happen to cancel with one another. So I'm not going to add or subtract anything on the outside. The rest of this process is now solving for y, because now I have a single y value I can solve for y. So I'm going to square root both sides. Don't forget your plus or minus. That means plus or minus the square root of x is equal to 2y minus 3. I'm going to add 3 to both sides. I'm going to put my next step up here. That'll give me 3 plus or minus the square root of x is equal to 2y. I divide both sides by 2. And that means, instead of y equals, I'm going to say f inverse of x is equal to 3 plus or minus the square root of x all over 2 as my final solution. The last thing I want to make note of. Now this has a plus or minus. I told you in the past, plus or minuses do not exist for functions. And that is also true here. Plus or minus is our shorthand way of saying there's two things here, one positive, one negative. That means that this is technically, f inverse is technically a combination of two different functions. One that has a plus sign, one that has a minus. That means technically, I cannot call this an inverse function. I would have to call it an inverse equation. In the past, when I said don't put the plus or minus, that was because we were trying to derive inverse functions. Here, we're trying to algebraically solve for the inverse equations. Now, the reason I'm delineating between the two is because in higher levels of mathematics, you're going to get access to newer tools, and some of those tools will have as a prerequisite that they only apply to functions. They do not apply to all equations. This is one topic where understanding that delineation is really, really critical, specifically calculus. They will use that delineation a ton. So I want to preface this and kind of bring up that topic. They will bring it up again in calculus, but just so it's not brand new. You see a plus or minus, it is not a function, it's an equation.